Hi guys, what's the crack? In this video, we're going to go over discovery of the nucleus. So what did these guys figure out and how do we get an approximation for the nuclear size, nuclear radius? So hopefully we remember from our GCSEs that Dalton was your first man to come along, our first scientist, our first boy. And he said that he thought that atoms were basically just a sphere. Okay, so you think about a football or sphere. He just thought they can't be divided into anything smaller, they're just solid spheres, like a football. J.J. Thomson came along and he said, no, he said, I think it's going to be a solid sphere, so still a solid mass like a football, but he thought there's going to be these negative electrons scattered within that mass. So again, what he said is we're going to have this positive mass, so a solid mass, and we're going to have those negative, so just write in positive, plus for positive, and negative electrons scattered within it, okay? So then what Rutherford came along and he said, if this is really the atom, we're going to test it. So what he did was he took alpha particles. And we know what alpha particles are from our year 12 physics, from earlier physics. If you don't, just look back at our previous videos when we did about stable and unstable nuclei. But we know an alpha particle is a helium nucleus, so 4-2. Okay, it has to be the nucleus, remember, because there's no electrons there. So remember, alpha particles, they have a relative charge of +2 because what they have is our 2 protons inside it. So what he did was he took an alpha particle and he fired it at this gold nucleus, this gold atom. And he thought if it was a solid mass and I fire these alpha particles at it, they should just all hit and collide with that solid mass and then be bounded at different angles. But what actually happened was that when he fired these alpha particles at that gold nucleus, at that gold atom, he saw that most of the alpha particles actually went straight through. So what he saw was actually most of the atom is empty space. So he found that most of the atom was empty space. He then saw that very few of them, but some of them, what happened was they got rebounded by angles greater than 90 degrees. And the only reason they get rebounded is because if I've got something that's got a positive charge, it's going to get repelled by something that's also positive charged. So he discovered that there must be a small nucleus and that the nucleus is positively charged. Okay, because again, he saw that some of the alpha particles got repelled. So what he did then was he found out that distance of closest approach. So what he found out was the distance of closest approach. So we got an approximation for the size of that nucleus. So again, if my dotted line represents my atom, we can see that most of the alpha particles went straight through. If we look at our alpha particles, because we're looking at distance of closest approach to get approximation of nuclear, they went in and then they got repelled away. They got repelled by that positive nucleus. So again, we're saying that this is the atom. So the alpha particles are going to go in and then get repelled away from that positive nucleus. So you see what I said there again, that we got an approximation for that nuclear size. We can see it's too big because the alpha particles can never actually hit that nucleus because they want to get repelled away. So we get approximation for the size of that nucleus, but it's too large. So how do he approximate the size of a nucleus? So what he did is let's say we've got an alpha particle being fired with 768 mega electron volts of energy. I know that an electron volt I can convert into joules by multiplying by 1.6 times 10 to the negative 19. So if I've had 768 mega electron volts, I have 768 times 10 to the power 6 electron volts. And all we need to do is multiply by 1.6 times 10 to the negative 19 to get that number in joules. So 768 times 10 to the power 6, because it's mega electron volts, we're multiply by 1.6 times 10 to the negative 19 to get that number in joules, which is going to be 1.23 times 10 to the negative 10 joules. So that's much energy he fired the alpha particle at my gold nucleus with. If the alpha particle is moving, we know that energy there is my kinetic energy. So if the alpha particle has loads of kinetic energy and what's happening is it's moving towards my nucleus, we know that that alpha particle is going to start to slow down. So my alpha particle is going to start to slow down, 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 until eventually it gets repelled away. And the reason it slows down is because that repulsion, because that electrostatic potential energy of repulsion. So I need to think about what is the energy here that's causing that, that's transferring from the kinetic energy into that electrostatic repulsion energy. And what I can think about is around my nucleus, so again, around my gold nucleus that's positively charged, we know we're going to have those potential lines. So this might take up my electric fields topic. So I know that potential line is equal to 1 over 4 pi epsilon naught, and it's going to equal to Q over R. That's the potential line. But I don't want to relate it to potential, I want to relate it to energy. So I can also see on my data sheet that potential is equal to the work done per unit charge to bring that charge from infinity to a point in the field. So just remember to revise your electric fields topic in my earlier videos and the earlier lessons if that's going to help you out. So to get to a work done or an energy, we do our potential times by our charge. So to put this into an energy of what the energy is here, we're going to say our energy is equal to 1 over 4 pi epsilon naught Q1 Q2 over R, whatever that distance is there, that distance of our nuclear radius R. So what we can do now is that we can equate them. We can say that our energy, which is 1.23 times 10 to the negative 10, goes all into that energy because of repulsion. So it goes into 1 over 4 pi epsilon naught Q1 Q2 over R. And that R again is our approximation for that nuclear radius. So what do we put in for our charges? Hopefully again we're thinking our alpha particle has a +2 charge, a relative charge of +2. So what that really is 2 times 1.6 times 10 to the negative 19. And we said we've got a gold nucleus, and I told you here it's got 79 protons. So that charge there is going to be 79 times by 1.6 times 10 to the negative 19. So we can just square that number. Okay? So what we can do then is rearrange to solve what that nuclear radius is. So what nuclear radius is. And our value for epsilon naught is on your front of your data sheets. So again, what they did was they got approximation for the size of that nucleus. Other scientists. So other scientists then was Bohr. Bohr came along and he said the nuclear model from Rutherford's not quite right. Because Rutherford said, yeah, we're going to have a positive charged nucleus, but we're going to have these electrons basically orbiting that nucleus. Okay? But Bohr came along and said these electrons are actually orbiting in shells, in specific energy levels. Okay, so Bohr came along and said that our electrons are in shells. Okay, so we've got my positive charged nucleus with my electrons in my shells. Chadwick came along and what he said was inside that nucleus is actually things even smaller. That nucleus is positively charged because inside there we have both protons and we have neutrons. So he was the first person to use the word protons and neutrons.